So in this part, we'll be seeing nucleophilic substitution reaction at saturated carbon atom. This particular part would cover the various types of nucleophilic substitution reaction and the two different mechanisms of nucleophilic substitution, that is unimolecular nucleophilic substitution as well as your bimolecular nucleophilic substitution mechanism. To start with, we should know what a nucleophile means. A nucleophile is any electron-rich species, or I can say it is a negatively charged or neutral charged species which can share a pair of electrons or which can donate a pair of electrons to an electropositive center. Okay, so nucleophile means it has to be electron rich and it goes in search of electron deficient species. So this is usually negative charge but sometimes also neutrally charged, but it should contain a lone pair of electrons, an unshared pair of electrons that can be donated to the electrophile. Okay, so nucleophilic substitution reaction means substitution of nucleophile in a particular reaction. Okay, this is one of the most extensively studied heterolytic type of reaction. Now, what do you mean by heterolytic? Suppose I break a bond, for example, CC bond, okay, and if there is not equal distribution of electrons between both the atoms, then that would be called as heterolytic cleavage. Okay, in this respect, you would have studied homolytic cleavage, which means when a bond is broken, there is equal distribution of electrons on both the atoms. Okay, so this particular reaction is relevant with respect to the heterolytic cleavage. Okay, so it's one of the most extensively studied heterolytic substitution reaction in saturated compounds. Now, what does saturated compounds mean? Saturated means you know that the valency of carbon is 4. Okay, so if all the valency, suppose all the bonds of carbon are singly bonded, okay, suppose I have carbon which is singly bonded, then I say that it is completely saturated. Okay, suppose I have a carbon which is multiply bonded to another carbon, okay, then in this case I would say that this particular molecule is unsaturated. Okay. Now, what are the types of nucleophilic substitution reaction? So we'll say it's SN2, which is also known as bimolecular nucleophilic substitution. Then there is your SN1, which means unimolecular nucleophilic substitution, and SNI, which means internal nucleophilic substitution. Okay, what you will be seeing later on is that your SN2 reaction is a one-step process, whereas SN1 reaction is two-step process. Well, intramolecular catalysis or SNI reaction is not so common, but still we will be seeing the cases where this particular mechanism is observed. Okay, now let's move on to the mechanism of your SN2 reaction. First, we should know that how this name SN2 came. Okay, so this particular symbol was introduced by the scientist Ingold in 1928. SN2 means substitution, nucleophilic, bimolecular. Okay, 2 means bi. Okay, so it is bimolecular. This particular mechanism takes place in one step. Okay, so this reaction takes place in just one step, and almost all your nucleophilic substitution reactions are characteristic reaction of your alkyl halides. Okay, so the major substrate over here is your alkyl halide. In this case, this is your methyl bromide, and this OH minus is the nucleophile, which can also be called as an incoming group. Okay, this bromine atom will be leaving, and hence this is called as the leaving group. Okay, so OH minus is the incoming group, Br is the leaving group, and this alkyl halide is the major substrate that is involved during the reaction. Okay, so when I talk about the mechanism of this reaction, as I told you, this takes place in one step. Okay, but here I see there are two arrows, which means there are two steps, but no. There is only one step, and this particular reaction proceeds via a transition state. Now, what is this transition state? A transition state is a state in which the molecule has very high energy. Okay? This particular molecule has a very short life, that is, it cannot be isolated from the reaction. Okay? So, we can just say that it is under transit. Okay? Once this is formed, this is going to give you your product, and you cannot isolate this particular transition state. Okay, so now we'll see how the reaction takes place. So what happens? You have your carbon, which is attached to your bromine, and this particular carbon is the reaction site. Okay, now this carbon would carry a partial positive charge because of the presence of bromine, which is electronegative in nature. So what does electronegative means? This bromine has the tendency to attract the bonded pair of electron towards itself. Okay, so if I say it attracts the bonded pair of electron, I am talking about my bromine attracting electrons. As a result, there would arise a partial negative charge on bromine and a partial positive charge on your carbon. Okay, so due to the presence of an electronegative bromine atom, this carbon gains a partial positive charge, or else in other words I can say this is a bit polarized because of the presence of an electronegative group. Okay, now this nucleophile, which is the incoming group, would attack any center which is positive, because this has a pair of electrons and it wants to donate its electron pair to a positive center. This has to attack your carbon atom. Okay, now the point to be noted is this particular nucleophile attacks your carbon atom not from the side where your bromine is situated. Why is it so? Because bromine is also rich in electrons. It has its own electron cloud, and OH minus is also rich in electrons. Suppose this were to attract from the same side, then the electron cloud over bromine would repel the electron cloud over your hydroxyl ion. Okay, so the only possibility is that this OH minus has to attack the carbon from the rear side, and that is what happens. Okay, the OH minus attacks the carbon from the side opposite to the side of your bromine. Okay, and as a result, you would see a transition state something like this. In this transition state, you will see that your central carbon is attached to 5 different groups. Okay, over here, the COH bond is not completely formed and CBr bond is not completely cleaved. So, as soon as your OH comes closer to your carbon, this bromine starts moving away with its pair of electrons. Okay, and that is why in the transition state you see that there is partial bond between your OH and your carbon and a partial bond between your carbon and your bromine. Okay, so once this OH completely transfers its electron to the carbon and forms a bond, in other words, I cannot say it completely transfers. Okay, when this forms a bond with a carbon, then bromine has to go away with its pair of electrons. In other words, when OH minus starts donating its pair of electron to carbon, then bromine, the valency is satisfied, right? So bromine has to leave, and because this is electronegative, it would leave with its a pair of electrons, the bonded pair of electrons. And hence, in the product, I will be getting Br minus and your alcohol. This is your methanol that is formed during the course of the reaction. Now, this particular step, this reaction proceeds in a single step, which means the reaction is concerted in mechanism, okay? And because this step is also the slow step and rate determining step, and the number of molecules involved in the rate determining step is 2. That is 1 with respect to your alkyl halide and 1 with respect to your nucleophile. So the total number of molecules that is involved in this particular slow step is contributes to the rate of the reaction. So how can I write the rate of the reaction? I can write the rate of the reaction as K. K is the reaction constant, rate constant, into the concentration of your alkyl bromide into the concentration of your nucleophile. Okay, so both the concentration matters equally, and hence this reaction is called as bimolecular nucleophilic substitution reaction. Okay, so your take home is nucleophile attacks the substrate from the back side and the leaving group leaves. Okay, so you get your product, which is a substituted product. Okay, and since there are 2 molecules involved in the rate determining step, this particular reaction is bimolecular nucleophilic substitution reaction. Now we will see what is unimolecular nucleophilic substitution. Okay, like I told you for SN2 reaction, the symbol SN1 reaction was also introduced by Ingold in 1928. Okay, so this SN1 means 1 is for unimolecular, N is for nucleophilic, and S is for substitution. So this is substitution, nucleophilic, unimolecular, which means the rate determining step in this particular reaction will contain only one substrate, and now we are going to see which one. Okay, so as I told you, the symbol SN1 was introduced by Ingold in 1928, and this particular reaction mechanism proceeds via 2 steps. Okay, so this reaction contains 2 steps, and the rate determining step is the slow step, which is the formation of your carbocation. Okay, so now let's see what is the mechanism of the reaction. So you see over here what happens. This is a tertiary butyl bromide. So the starting material is your tertiary butyl bromide. Here the leaving group is again bromide, and the nucleophile is your Cl minus chloride. Okay, this is a chloride ion. So in the first step of the reaction, you see that carbon and bromine bond gets broken. Okay, so in the first step, breaking up of your carbon-bromine bond takes place. As a result, carbon carries a positive charge and bromine leaves with a negative charge. Due to the loss of electrons to the leaving group, carbon becomes positive, and this is called as a carbocation. Now, once this carbocation is formed, your chloride will come and attack with its pair of electrons on the positive carbon, giving you your nucleophilic substituted product. Okay, so in the first step, breaking of CBr bond takes place, and in the second step, the nucleophile attacks your carbon, that is your carbocation, to give you your substituted product. Now, out of these 2 steps, the first step, that is breaking of CBr bond, is the slow step, and hence this slow step is also the rate determining step of your reaction. And in this particular step, only one substrate, that is your alkyl halide, is involved, and hence the rate of this reaction can be given by the equation rate is equal to K into concentration of your alkyl halide. In this case, it is alkyl tertiary butyl bromide. Okay, so the rate of your SN reaction can be given as K. K is the rate constant, and this square bracket denotes that it is the concentration of your Rx, your alkyl halide. Okay. Now, one important conclusion that we make from this particular reaction is that your reaction proceeds via a carbocation intermediate. Now, why do I say it's an intermediate and not a transition state as I told you in your SN2 reaction? That is because this intermediate has a longer lifetime, okay? And people have even isolated certain derivatives of this carbocation, okay? For example, Daubin et al., that is he and his co-workers in 1960 obtained salts of triphenyl methyl carbonium as perchlorate. Okay, so if I substitute this methyl group, all the three methyl group with phenyl group, then that becomes triphenyl methyl and carbonium, because carbon carries a positive charge. Okay, and that has been isolated in the form of its salts as perchlorates and as fluoroborates. Okay, so what do we conclude? We conclude that SN2 reaction is a single step process wherein OH minus, your nucleophile, attacks your carbon and bromide leaves the carbon simultaneously, and the rate determining step is dependent on the concentration of your nucleophile as well as the concentration of your substrate. Hence, it is bimolecular and it follows second order kinetics. But in case of SN1 mechanism, it proceeds via two steps, and the first step, that is formation of your carbocation intermediate, is the rate determining step. And once this carbocation is formed, it quickly takes up your nucleophile, and this is a fast step and gives you your substituted product. That's it in this part. We'll see the factors that affect the nucleophilic substitution reaction in the next part. Thank you.